Welcome to Deep Learning on Text and Images. Deep learning has shown remarkable success in processing and understanding unstructured data, like text and images. In this module, we will explore how deep neural networks can be leveraged to build intelligent systems in the domains of natural language processing and computer vision. Get ready to dive into the exciting world of deep learning on text and images. We will start with the agenda and course overview. Then, we will review some key machine learning concepts, including regression, optimization, regularization, and text and data representation. Let's start with an overview. This course consists of 3 modules. The first module, Introduction to Neural Networks, delves into layers and activation functions, neural network learning principles, examples using PyTorch, and neural network engineering concepts. The second module, Natural Language Processing, explores common NLP domains, text pre-processing and vectorization techniques, word embeddings, recurrent neural networks, RNNs, application examples, and an introduction to transformers. The third module, Computer Vision, focuses on common computer vision domains, convolution concepts, convolutional neural networks, CNNs, modern neural network architectures, fine-tuning methods, and transfer learning approaches. This structured outline provides a comprehensive roadmap for the course, covering fundamental concepts and practical applications in neural networks, natural language processing, and computer vision. Before we proceed with learning about neural networks, we will begin with a review of key ML concepts. Namely, this includes linear and logistic regression and their evaluation metrics, optimization and gradient descent, overfitting and regularization, and text and image representation. We'll start with regression. Regression is a popular type of supervised learning problem. Regression aims to learn relationships and correlations between input features and a continuous output variable, with the goal of predicting the continuous output variable. For example, the price of a book might depend on a certain combination of the number of pages, days since being published, language, and number of reviews. The scatterplot shows a simple linear regression model. If you assume that the relationship between the sale price of a book and the number of pages is linear, in other words, as the number of pages increases, the price of the book increases, the line of best fit is a straight line. Some ML algorithms that you can use to build regression models include linear regression, k-nearest neighbors, KNN, decision trees, and neural networks. In ML, model evaluation is the process of assessing the performance of a trained model on a set of validation data. This involves comparing the model's predictions or decisions to ground truth labels or reference data, and using various metrics to quantify the model's performance. Errors are the differences between the target values, yi, which is represented on the graph by black dots, and the values that were predicted with the regression model, yi, which are the predictions that sit on the regression line. 4 regression metrics look at the overall model errors, and the next slide will describe these metrics. You can look at these errors as absolute values or squared values, so that the negative errors can contribute meaningfully to the overall sum. The first metric, mean squared error, MSE, is the average of the squared errors. Because MSE squares the error differences, it penalizes even the smallest errors, leading to overestimation of how bad the model is. Another metric is root mean square error, RMSE, which is the square root of the MSE. This is widely used for regression tasks. While MSE reports errors in units squared, RSME reports errors in the original units, which makes it easier to interpret the error. You can also look at the mean absolute error, MAE, which is the average of the absolute differences between the target values and the values that the model predicted. Being a linear score, all the individual differences are weighted equally, so MAE is more robust to outliers and does not penalize the errors as extremely as MSE. Finally, you can use R-squared, which helps compare the regression model with a constant average baseline model. It predicts averages for all data points. This metric tells how much better the regression is compared to the baseline model. With other metrics, lower scores are desirable. R-squared is different. Assuming that the ML model will always perform better than the baseline, average model, R-squared will take values between 0 and 1. If the model didn't improve at all over the baseline model and produced the same errors, then R squared is 0, lowest. For the best regression model, which doesn't have errors between the predicted and actual values, MSE equals 0, R squared will be 1, highest. While MSE is the most preferred metric for regression tasks, as with other areas of ML, there isn't a clear choice of which metric to use. Best practice is to monitor a few, depending on the business problem and the dataset. If you'd rather know whether a particular book is fiction or nonfiction, that would be a classification problem. Classification aims to learn the relationships between input features and an output variable, with the scope of separating the data into classes or groups. The main difference between regression and classification is that the output variable in regression is numerical, or continuous, while the output variable for classification is categorical, or discrete. The example on the slide shows a binary classification scenario, that is, there are only two classes. Some ML algorithms that you can use to build classification models are logistic regression, support vector machines, KNN, decision trees, and neural networks. How do you evaluate a classification model? You can judge the performance of the model and its associated errors by examining correctly classified cases compared to incorrectly classified cases. Consider a binary classification task to determine the genre of a book. You can compare the predicted results to the known values. Mark any correct prediction as true and any incorrect prediction as false. Record the results in a confusion matrix. The name reflects that the classifier is sometimes confused and makes mistakes. In this binary classification example, the matrix has 2 rows and 2 columns. The columns represent the predicted class labels, and the rows represent the actual class labels. Each cell contains the number of predictions made by the classifier that fall into that cell. This matrix makes it easier to observe relationships between the classifier outputs, and examining the confusion matrix usually indicates whether the classifier is bad or good. In this case, the classifier seems to have done a good job of assigning most data points to their correct classes. A perfect classifier would correctly predict all cases, so high numbers would stay on the diagonal that covers true positive and true negative areas, and nothing would fall off this diagonal into the false/error tiles. While the confusion matrix contains all information of the outcomes of a classifier, it's rarely used for reporting results because it's difficult to compare and discuss. Instead, some overall numerical scores are extracted from the confusion matrix. To calculate the accuracy of an ML model on a training set or validation set, you can use the following formula. Accuracy equals true positives plus true negatives divided by true positives plus false positives plus true negatives plus false negatives. We will continue with an optimization review. ML models aim to take in the model features and match the model target. In reality, almost all ML models take in the model features and make model predictions that rarely match the model target exactly. Some error occurs. The key focus of ML is learning better models where the overall model error gets smaller, ideally as small as possible. To understand how the loss function is applied in neural networks, let's briefly review how it works in other areas of ML. The loss function may also be called the cost or objective function. It expresses the overall model error, so the optimization process tries to reach the minimum value. Loss functions are used in neural networks in the same way that they are used for the classical ML linear regression model. Measure the model predictions against actual labels to evaluate how well the model is performing, and measure the optimization that is applied during the learning process. For binary classification problems, the logarithmic loss function is a good choice because it outputs values in the range 0 through 1, which can be interpreted as the probability for each class. For example, an output value of 0.89 suggests an 89% chance that the data point is class 1 and an 11% chance of being class 0. For regression, a good choice for an output activation function is the linear function, as seen with linear regression, or the rectified linear unit, ReLU, if negative values are not of interest. Remember, to measure the estimation quality of a neural network, you compare the true values, y, to the predicted values, y hat, by defining a loss function, LW. Gradient descent is an optimization algorithm that searches for weights to minimize the loss function. To summarize, this is the gradient descent method. It uses gradients to find the minimum of a function iteratively. Specifically, you take steps that are proportional to the gradient size toward the minimum, in the opposite direction of the gradient. Gradient descent algorithm, from any initial point W, presumably not at the minimum so the gradient isn't zero, move toward the minimum. Update the W by small or large steps in the opposite direction of the gradient. The size of the update is controlled by the step size parameter, also known as the learning rate. If the step size is too small, the algorithm might take a long time to converge or might never reach the global minimum. More complicated scenarios can also occur. For example, when the step size is too large, the function might jump back and forth over the minimum and never converge. Now, we will review regularization. Low scores on the training dataset, high regression errors, R-squared that is negative or close to zero, or classification metrics close to zero, are indicators that the model didn't learn much. It is not fit to do the task it is training for. The model is underfitting. This means that the model did not capture the important patterns in the training dataset. An underfitting model does not perform well during training and is not expected to generalize to new data. Adjusting model hyperparameters could help to address overfitting. You might also need to return to the data processing or feature engineering steps in the lifecycle. Sometimes, switching to another ML algorithm altogether is a better solution. At the other extreme, and more common in ML, is when the model works well on the training dataset but doesn't work with the validation or test dataset. How can this be? The model learns everything about the training data, including every detail and noise in the training data, but this can negatively impact the performance of the model on future data. All those details and noise that the model picked from the training data as rules might not apply to new data. The model didn't find generalizable patterns, so the model might not be able to generalize. This describes the trickiest but most common problem in ML, overfitting. Several techniques are available to lessen the chance of, or amount of, overfitting. One method is to reduce the generalization gap that is observed between performance scores on training and validation datasets. At the very least, you need to ensure that you train and validate model performance on different datasets. Ideally, you want to build ML models that perform somewhere in between the two extremes of underfitting and overfitting. This ideal state is what a good, appropriate fit would be. To get an appropriate fit, you need to compromise on model performance on the training set so that the model pays less attention to the noise in the dataset and concentrates more on the patterns that can be generalized. This will help the model to successfully make predictions on future unseen data samples. The validation set is helpful for the following reasons: building models on the training set and validating on the validation set, monitoring performance metrics for validation, in particular, aiming for the model that performs good enough on both. Capturing the model that gives the best validation performance. Other than cross-validation, you can use many other ML techniques and ML algorithms to find appropriate fit models. These techniques and algorithms include the following: early stopping. When you train an ML model iteratively, you can measure how well each iteration of the model performs. Until a certain number of iterations, new iterations improve the model. However, after that point, the model's ability to generalize can weaken as it begins to overfit the training data. Regularization. Regularization refers to a broad range of techniques for artificially forcing your model to be simpler. Ensembling. Ensembles are ML methods to combine predictions from multiple separate models. Neural networks are prone to overfitting. Adding more layers and increasing the number of neurons in the layers can lead to overfitting faster. Regularization helps you train ML models that generalize better beyond their training datasets. It is used to reduce overfitting. The appropriate fitting is where the model can learn the patterns that are present in the training data without memorizing noise that is always present in datasets. Recall that text and data representation refers to the ability of machine learning models to effectively encode and process data in different forms. When tabular data is used in ML, the rows of the table represent each data sample. The columns represent each feature and the label. In this table, the features include month sold, year sold, and genre, while the label is the sale price. Each row is a data sample. Another of the most commonly used types of data in ML is image data. Each data sample is an image that is stored as a file. Features are determined by pixels and their relationships to each other. An example label is what kind of animal is in the image. The last type of data that is commonly used in ML is text data. Each data sample is a piece of text. It might be a sentence, chapter, or document. The features are text characters or words. An example label is if the text expresses a positive or a negative sentiment. In the example on the slide, which reads, "This book is pretty good. I would recommend it to my friends," there is a positive sentiment. In the next lesson, you will learn the basic components of neural network and how it implements ML. We will explore a single-layer network called a perceptron, which is represented by a single neuron. Then, we will cover how to use a perceptron to solve a regression model. Thank you.